our study of rates of change and slope, which reviews linear equations. Now, you just watched a video that shows real life applications of rates of change and slope. But what is really not limited to those ideas just in that video. There are a lot of places in real life that use rates of change, but let's review the basics of it. All right, so a rate of change is the measure of how much a quantity changes on average relative to the change in another quantity. So you're comparing, like a ratio, the idea of two quantities changing. All right, now in algebra, we study rates of change, but we call them slopes because we look at the difference in the y values on a coordinate plane and we look at the difference in the x values on the coordinate plane. So that's measuring the quantity of how two different values are changing and comparing those to each other. So the slope of a line in algebra is the ratio of the change in the y coordinates to the corresponding change in the x coordinates. All right, so how does that look in a formula? So again, we're comparing that rate of change as the change in the y coordinates and the change in the x coordinates. And we look at how slope is developed. Now in algebra, we use m to represent our slope for our equations when we look at the formula for slope-intercept form or point-slope form. But what the slope is representing is the change in the rise over the change in the run. So that's your y coordinates and your x coordinates on a coordinate plane. So remember back to here is our coordinate plane. This would be our x-axis. This is our y-axis. So it's a comparison of the rise, or the change in those y coordinates, compared to the run, which is the change in the x coordinates. All right, so when you take some higher level science courses like physics, they're going to denote that change using this delta formula. And in science, we just represent that Greek letter delta as representing change in. So rise means the change in the rise, which is our delta y, and run is the change in our x values, which is delta x. All right, now this is the formula that's going to look familiar to you because this is how you calculated slope in Algebra 1, where you actually subtract the difference between your two y values and then divide that by subtracting the difference of the x values. When we get into function notation just replaces those y's with our f of x's. So if I have a set of points x sub 1 and x sub 2, then we compare the difference of our y's by f of x sub 2 minus f of x sub 1, which is just the replacement of y sub 2 and y sub 1 with our function notation. All right, so those are our formulas for slope. Again, this should just be a review for you at this point. So let's look at this idea of the path this skateboard would take. So you can see our coordinate plane with our x-axis and our y-axis, and you can see that the path of the skateboard is crossing these two defined points, which the first one gives me an x sub 1 value and a y sub 1 value. And the second point would be x sub 2 and y sub 2. Now, does it matter which way I label those? No, but you always have to start with the same set of points first. All right, so as I calculate the slope of this skateboard, I'm going to start with my y sub 2, and I'm going to start with 3, and I'm going to subtract from that y sub 1, which is 1. And then since I started with this set of ordered pairs first, I'm going to start with it second in the denominator, and I'm going to subtract x sub 2 minus x sub 1, which is a negative 3. Now when I calculate this math, I get 3 minus 1 is 2. I get 7 minus a negative 3, which we know really means plus, and that gives me 10. So the slope of the skateboard would be reduced to 1/5. Notice that it's positive because it's going up the hill. So it has a positive slope. So it's a positive change on the rise and a positive change on the run. We can also, because this is graphed for us nicely, we can also count that change. So really, I can count up, rising 2, and it's running 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can see the rise is 2, run is 10, which reduces to our slope of 1/5. Okay, so you've seen me do it on the graph and you've seen me do it using the formula. Now let's look at this example when it's not graphed yet. This is find the slope of the line that passes through the points 1, 3, and -2, -3. So I could do this actually without seeing the line first because I can utilize my formula y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So I just verify which set of points I want to start with. Again, it doesn't matter as long as you start with the same points on the top that you do on the bottom. So if I start with my y sub 2, I'm going to have -3 minus 3 on top, and then I'll have -2 minus 1 in my denominator. When I simplify that math, that gives me -6 over -3, or this line should have a slope of 2. All right, so I'm going to graph this real quick. So I'm going to plot out 1, 3. I'm going to plot out -2, -3. And if I draw a quick line through those 2 points, again, my line is going in a positive direction. And if I test it out, I can go really up 2 over 1, up 2 over 1, up 2 over 1, and I can continue that slope all the way up. All right, so now let's apply this to a real life problem. In college admissions, it says, in 2016, 31,388 first-time college students applied to a state university. So I'm going to turn that into an ordered pair. So I have in 2016, there were 31,388 applications. In 2014, 25,949 students applied. Find the rate of change in the number of first-time college students applying for admission. So rate of change is synonymous with our slope. So I'm just going to calculate the slope of these two ordered pairs. So that's going to give me, if I call this x sub 2 this time, so you can see I didn't start with the second one, and that's okay. Divided by, but I have to start with the top one on top since I started there, or on the bottom since I started there on top. So now I do a quick calculation. So when I take 31,388 minus 25,949, I get 5,439. And the years 2016 minus 2014 gives me 2. So that gives me approximately, because this is not going to divide out evenly, but, and you'll see why in a second, 2,719.5, showing you a half of a student. We know we really can't have half of a student, but that over 1. So our rate of change means that I have 2,719.5 students per year. So you can see the comparison of two different quantities. Our quantities here would be comparing students and years together to find our rate of change. All right, the last example I have for you is a business example, and this time I do give you the graph to this. It says refer to the graph below, which shows the data on the fastest growing restaurant chain in the US during the time period of the graph. Find the rate of change in the number of stores from 1999 to 2004. Now you can see this graph is not exactly linear. It's close to having a linear trend, but it's not exact. So when we're doing this, we're just going to find the rate of change of these 2 years, so it's going to average out to be a linear slope. All right, notice that on our graph they abbreviated the years 99 and 04. Now we don't want to subtract it like that because it's going to look like there are 95 years between those. When we subtract it, we want to use the whole year. All right, I'm going to give myself some more workspace here, and I'm going to flip this slide. Whoops, nope. Actually, I forgot to leave myself an extra space, so we're going to do it right here. So our slope becomes in 99. Now you can see they didn't give us precise measurements in this example. So what I'm going to do is I'm going to estimate. I'm going to estimate that at 1999, there were about, I'm going to measure, it's a little bit over 5, so I'm going to say there were 6,000 fast food chains because this axis is based off of thousands. And I'm going to say in 2004 that we have roughly 33,000. So that gives us our 2 ordered pairs. And again, you and I might estimate these 2 totals differently. So we might not all have the exact same answer, but we should be close. All right, so let's do this quick math. 33,000 minus 6,000 and divide that by 2004 minus 1999 gives me a slope of about 5,400. Remember, our top is representing restaurants divided by 1 year. Oh, nope, that's going to be 5 years, sorry. And I messed up on my calculation because I'm giving you the whole thing. So this really was 27,000 divided by 5, and our slope then becomes 5,400 restaurants per year. I got a little ahead of myself looking at my notes. Okay, and that's how you calculate rates of change and slopes using 2 points or using a graph. So let's just review the idea of slope very quickly. So you can see 6 lines here, and I just want to understand not the exact value of the slope, but whether that slope would be positive or negative. So notice if I would pick 2 points on this slope, and I would go from one to the other, I would have to make a negative change and a positive change. So a negative divided by a positive would result in a negative slope. So going down the hill is a negative slope. Same thing here. If I pick 2 points to get from one to the other, I'd have to make a positive change and a positive change. So this line would give me a positive slope. All right, and this one tricks us up a little bit. If I pick 2 points on this line, my rise gives me a positive change, but my run is a 0 change. So if I take positive divided by negative, we know that we can't ever divide, or positive divided by 0, we know we can't divide by 0, so this gives us an undefined slope. All right, so a vertical line has an undefined or no slope. Our next example, this is a lot steeper, but it's going down the hill again. It's going to have 1 negative, 1 positive, and this is going to be a negative slope. And this horizontal line, this time my rise is 0, but my run is positive. And a 0 divided by a positive number is going to be 0. So this guy has a special slope. He has a 0 slope. And this last one, the rise is positive, the run is positive, so this is going to have a positive slope. So you can see down the hill is negative, up the hill is positive. A straight vertical drop is undefined or no slope. Down the hill, negative. Flat is 0 slope, and up the hill is positive.